So today we are going to study about Cayley-Hamilton theorem. So this theorem was given by William Rowan Hamilton and Arthur Cayley. So it says that every square matrix AN satisfies its own characteristic equation. So we are very well known about the characteristic equation of a matrix, of a square matrix, so that we can get by determinant of A minus lambda I, so that we will have characteristic equation. So it says that this theorem says that every square matrix A satisfies one characteristic equation. So that means if we put matrix A instead of lambda, so that equation also satisfies. So let's see what I'm saying about. So we have this characteristic polynomial. So we have this characteristic polynomial of n cross n matrix is defined by this way, and then we have this characteristic polynomial PA of lambda will be determinant of lambda I minus A. So this will be our characteristic polynomial. So now so I can expand this and I can write in the monic polynomial like that. PA of lambda will be like that, like this equation. So like this equation, we have this PA of lambda. This will be our characteristic polynomial. So now by Cayley-Hamilton theorem, we can replace lambda by A since it satisfies this characteristic equation. So we can write PA of A will be lambda will be replaced by this A. Then this will be A power n minus 1. This will be A, and this since we are calculating this all in matrix form, so we have this constant C0 time nth order matrix since A is of n cross n order matrix. So this will be our Cayley-Hamilton theorem. So now we can see some of the application. So and some application in detail and some application we can just see can be used further. So first application is matrix inversion. So suppose if you have to find A inverse, so you can easily find that from this characteristic equation by using Cayley-Hamilton theorem. So it will be very easy. So now second is to compute higher power. So if you have to compute like A power n, so you can easily calculate it up to calculating the power A raised power n minus 1. So you can just adding up and then you will get this higher power. So now further is eigenvalue computation. So if you have to compute eigenvalue, so this theorem have application. Further, control theory that can be used to compute state transition matrices in linear systems. So that will be very helpful. So in solving differential equation, it is quite easy for linear system. And then from this nth order linear system, you can put them into the matrix, then in square matrix, and then you can easy to solve this equation. Then symbolic computation. So if you like it will be reduced higher power of A to similar to polynomial form. So like these kind of computation will be easy in that case. So first we will see some application here and further are for your use. So I consider this example of a matrix 2 cross 2, and this will be A is in this example we will verify our Cayley-Hamilton theorem, and then we find A inverse and A power 3. So first is characteristic polynomial, which is given like that, determinant of lambda I minus A. Then we will easily find that determinant that will came out to be lambda square minus 4 lambda plus 3. So now what you see, so verifying that we will have to show that P of lambda A P of A is equals to 0, that we have to show. So if we can show P of A is equals to 0, then we will have this verification of Cayley-Hamilton theorem. So from this we will have characteristic polynomial like that. So then by using Cayley-Hamilton theorem, we will have this equation A square minus 4A plus 3I. So now we compute A square, so we will have A square like that. Then we compute this minus 4A like that, then 3I will be this, and we just adding up P of A will be your this. So it comes out to be 0. If this equals to 0, so then P of A is equals to 0. So then our proof for like verification for Cayley-Hamilton theorem is done. So we have done with this proof. So now we have to find this A inverse, then A cube. So we will go to A inverse, and then we call it matrix inversion. For that we will use characteristic equation. So like that is equals to 0. So we take a common from first two terms, so we have this kind of equation. We put 3i on the other side, right? And we just take minus common here, and that will be a times 4i minus a, and then we will have this a inverse in we will have this a inverse like that. We don't have to go through this classical method the way we find a inverse, so we can have this method also. Okay, so like we do not to find the adjoint of matrix A and then divide by this determinant, so we just simply calculate it through this Cayley-Hamilton theorem. And then we can compute higher power also by using this Cayley-Hamilton theorem without much computation. So we will have this characteristic equation like that. So from that we can find a square is 4a minus 3i. So we will use that. So if we have to compute a3, so then we can write this a3 to be a times a square. Then a square is equals to this. So we just put this value a square here. So we'll have this. And now 4a, and we first compute this a times 4a minus 3i. So this comes out to be 4a square minus 3a. So this will we have now 4a square. A square we have already defined. So we again put this value and we compute 4 times this 4a minus 3i, then minus 3a, which comes out to be 3a minus 12i. So that is very easy to compute. So we have computed this a cube without multiplying this this kind of matrix. So we'll have this come out to be easy for us. So these are some application. I hope these are useful for you, and thank you.